Greetings, grade 10 students. In this video, we'll be solving a problem that is related to conservation of energy. Now, before solving the problem, I want to emphasize that I have designed the problem by myself and I have created the problem by myself. What that means is that this problem is not on your books, okay? But it's just an alternative to the sample problem 4a in chapter 4, section 4.1. Okay, so it's a good alternate substitution that we can practice on, specifically on the conservation of energy concept. Now, let us proceed. So, P stands for problem. We have a problem. A 2.0 kilogram copper sphere is dropped from a stationary helicopter at a height of 400 meters. Alright, so we have a mass of the copper sphere and we have the initial height before it gets dropped. So based on this information, on this piece of information, we draw a picture of this problem. Always try to draw a picture, okay, or diagrams. Okay, so we have a copper sphere. It has a mass m that is equals to 2.0 kilograms. Now, suppose we have a reference ground, all right? Which eventually the sphere will get dropped upon to. Now, we label our initial reference height, this dotted line, as h initial equals to 400 meters, all right? And this reference as h final equals to 0. What that means is that the initial height before it gets dropped is at 400 meters, and finally when it strikes the ground or hits the ground, of course its height will become 0. Okay. Let us continue. It falls and hits a large insulated pad on the ground. So there's a insulated pad. Suppose this is the pad. All right. Of course, you may notice that the pad adds a little height, but no, we assume it's very thin in that hypothetical scenario, okay? As if it's stuck to the ground, okay? Now, coming to a complete stop, that's a very important information. It's a very great hint. So initially, before dropping the ball or the copper sphere, what is its initial speed? Of course, 0. So initial speed is 0 because we have just holding it at that moment. Now, as it hits the ground or strikes the ground, its velocity is also 0. So v final is also 0 as it becomes here. Okay? Now, assume the air resistance is negligible during the fall, alright? And 100% of the mechanical energy, that means the potential energy and the kinetic energy, lost upon impact is absorbed by the copper sphere. That means there is no leftover energy. As the copper sphere hits the ground, its internal energy will increase. In other words, it will get hot, or it will feel hot if you touch it at that specific moment, or at that particular moment. Okay, so there is no leftover fractional energy. Everything is 100% converted from mechanical energy to heat energy, or thermal energy, or internal energy, whatever you like it. Now, of course, this is the hypothetical scenario. In real life, some part of it will become sound, some part of it will become heat, and furthermore. Okay? There is no 100% mechanical energy transfer or conversion. Alright. Now, calculate the increase in internal energy of the sphere. So we are asked to find what is delta U. Alright? U represents the internal energy and the delta is the change in internal energy. Because obviously it's impossible to calculate U separately. We rely on calculating the change, the discrement change. Okay, so what do we do? Well, we write our equation, our main equation, the change in potential energy plus the change in kinetic energy plus the change in internal energy all adds up to 0. Now, what is the change in potential energy? Well, recall that potential energy is nothing but mgh, the mass of the object, the gravitational acceleration constant, or acceleration due to gravity, and the height, where it dropped from. Now, kinetic energy also in classical mechanics is equal to 1 over 2 mv squared. Okay. That's what we have. But notice, we have a delta symbol. So we have mgh final, mgh initial. 1 over 2 mv squared final, 1 over 2 mv squared initial. Alright, let's open these equations, or these expressions. Let me drag this to here. Okay, now, the change in potential energy, as we have stated, is mgh final minus mgh initial plus 1 over 2 mv squared final minus 1 over 2 mv squared initial. I have to drag them again. They create huge space. Okay. Anyways, now plus delta U is equal to 0. Okay, pay attention. We see that the final height is 0, right? That means this term will be just 0 or cancels out. Now mgh initial is not 0 because we have a number, g is a number, mass, we have the mass, so we cannot. Now, 1 over 2 mv squared final and 1 over 2 mv squared initial. We know that initially it has 0 velocity because it's on our hands before we drop it. Finally, eventually it will become to complete stop or comes to a complete stop. So the final velocity is also 0. That means we can just cancel both. Okay, so what we are left with is negative mgh initial plus the change in internal energy is equal to 0. Now we move this equation to the other side because we want to solve for the change in internal energy. We say internal energy is equal to nothing but mgh initial. Now what that means, this equation speaks. It resonates something, a deeper meaning of this problem. It says that the internal change or the change in internal energy, it is completely stored by potential energy. Or in other words, the potential energy, it's all converted to internal energy. There is no leftover energy. Okay? Alright, now let's just put the numbers in, or substitute the givens. Okay, so we say delta U is equals to the mass, which is 2.0 kilograms, times the gravitational acceleration, which is 9.81 meters per second squared. You can take 9.8, whatever you like. And the initial height, which is 400 meters. Now, if we calculate this, or multiply all of this, what do we get? Well, let's see. We get exactly 7,848 joules, or 7848 joules. Now, what does it mean, this number? Especially its positive number. That means the internal energy of this sphere will increase as it hits the ground. In other words, its temperature will increase. The average kinetic energy of the particles, of the molecules, will increase. Plus the potential energy as well. That's what it tells us, this number. But we are not focused, we are not basically trying to calculate the temperature for this problem. This is not our purpose or focus in here. But it will tell us that the object gets hot. If it were negative, this number was negative, then we would have labeled the change in internal energy as that the object becomes cold. Alright? Or it will feel colder. Or very cold. Okay? So that's it for this problem. Thanks for watching.